Welcome to the first video of the second chapter of the Crystal Clear Electronics 2 curriculum. In this part, we will learn about modern microcontroller types. In the first video, we will show you the most significant needs in the industry that are driving the development of contemporary microcontroller architectures. Our presenter is Viktor Vince, an electrical engineer who is currently leading a project on the development of implants at Neonos Limited.
Hello and welcome everyone. My partner today is David Vince, a mechanical engineer you met in the video of Chapter 4 of the Crystal Clear Electronics 1 series. This chapter will be unique since we are the only siblings among the presenters. You're already familiar with microcontrollers if you have read or watched the videos of the Crystal Clear Electronics 1 curriculum, 9th and following chapters. This time, you will get a much deeper insight. In the previous videos, we looked at how microcontrollers evolved and the path they have taken since ENIAC.
Rest assured, we're going to dive into some really interesting topics and move on to the tools we use today. In this video, we will show you the advantages and disadvantages of the different architectures.
These include a brief look at the design of ARM-based systems, and more specifically, the STM32 family of ST microelectronics products. David, before we start this chapter, why do you think this knowledge is important for someone who wants to use microcontrollers to solve a problem?
I think what you're getting at is that it makes a difference whether I want to open my bottled Coke in the summer heat with a screwdriver or a plasma cutter.
Or I know an even better one, a bottle opener. Microcontrollers are also target tools, and while most types can handle most tasks, the first step to an optimal and efficient result is to choose the appropriate controller.
So let's get started. Chapter 2 was written by Máté Prensperger and proofread by Gergely Lagler.
The industry is an interesting animal. I could best compare it to a lead-winged concrete owl, to quote a favorite comedian of mine. It's slow to adapt, which is understandable, given that with any new technology there is a learning period, which requires human and financial resources. We often hear, why change it if it works?
Exactly. A 30-year-old 600-ton press will still be a 600-ton press in 30 years.
This is absolutely true for a press machine, but a microcontroller has proven to be far less timeless. Why is that? The answer is simple. Because user needs are increasing. Everyone wants faster and smaller devices, and manufacturers are trying to meet this demand with more or less success. I'd like to highlight three main motivating factors. The demand for high-performance computing is increasing rapidly. It's now a common expectation among users to think that a device can do several things in parallel. This is often an illusion due to the high-speed operation of single-control electronics. The number of IoT, that is Internet of Things devices, is exploding. There's a need for devices that can constantly communicate in some way. General-purpose microcontrollers are being used for a very large number of applications, as the time to market is critical in today's accelerating economy. It's often more efficient to solve a task with one known microcontroller than to use several application-specific ICs, so manufacturers try to integrate as many functions as possible into a single microcontroller. Given these needs, we can see that it is no longer enough for a microcontroller to be able to add and subtract. Of course, older models could do more too. There's a need for hardware extension units, so-called coprocessors, for example, to perform complex encryption and signal processing tasks without using up all the processor's resources. The ratio between the amount of data to be processed and the time it takes to process has increased significantly. Just think of smart home devices or real-time signal processing devices such as guitar effects.
And don't miss the medical instruments.
Exactly. For example, the implant we're working on can detect and intervene in real time at the start of an epileptic seizure based on the patient's brainwaves.
So, in such an application, it also matters how fast a signal processing task can be performed and how much power it takes?
Yes, it does. Most of the great classical microcontroller architectures are based on 8-bit fundamentals. This is enough for many things even today. These microcontrollers are still suitable for applications with smaller memory and computing requirements. However, for computation-intensive tasks, where a 32-bit microcontroller completes in one clock cycle, we sometimes have to wait more than 4 cycles for the result in the case of an 8-bit one. As you could see in the previous video, Moore's law is still more or less valid today, meaning that the price of transistors is lower and we've made improvements in their size and power consumption as well. So the discussion above is only true with the same manufacturing technologies. The price and power consumption of modern 32-bit microcontrollers are now similar to those of the 8-bit microcontrollers available on the market. Some commonly used 8-bit microcontrollers include the Zilog Z80, the Intel 8051, as well as the Atmel AVR, all created in the 1970s, and today's microchip PIC. From these, the 8051 is the odd one out, the only one with a CISC instruction set. Today, the x86 architecture, which is typically found in PCs, still uses a CISC instruction set, while a significant portion of microcontrollers use RISC.
Alright, enough of the history lesson. What are the solutions that can be applied to a modern system?
Don't worry, it's coming soon. Perhaps the best known 8-bit controller family for hobbyists is the Atmel's Atmega, which can be found on most Arduino boards. All of these have 32-bit successors, but they are significantly less common than their 8-bit processors. In today's industry, ARM Cortex-M based controllers dominate the 32-bit market. There are emerging candidates, such as the X-Tensor cores used in the ESP32, favored by the Chinese industry and the world of hobbyists. Many manufacturers produce ARM-based microcontrollers, such as NXP, Microchip, or Silicon Labs, but it would be difficult to name another family of 32-bit microcontrollers with such extensive support as the STM32. Not only do they provide plenty of help in terms of software or hardware, ST also produces application nodes for many purposes. They also provide specific application nodes, not just for industrial use. Many hobby electronics enthusiasts also choose this microcontroller when they need serious computing power.
What microcontrollers have you used in your career so far?
After university, I started working with medical devices and always needed some kind of signal processing, so I used to work with DSPIC. But for the last 10 years, I have been using ST products almost exclusively. I don't want to let the cat out of the bag. You can find the details in the upcoming video. Until then, see you all!
Bye!